A network with 1,000,000 weights. How does each one know whether to go up or down? This is Forward Pass AI. In the last episode, we built a multi-layer network that could solve XOR, but we hand-tuned every weight ourselves. We chose the numbers, the network didn't. Today, the network tunes itself. The question is, how? Before the network can tune itself, we need a single number that captures how wrong it is. We call this the loss. The simplest loss for a single output is squared error. The loss L equals the variable y pred minus the variable y true, all squared. Why square it? 2 reasons. First, squaring removes the sign. Being wrong by +2 and being wrong by -2 are equally bad. Second, squaring makes large mistakes hurt disproportionately more than small ones. A mistake of 2 costs 4. A mistake of 4 costs 16. The network is motivated to eliminate big errors first. At error equals 0, the loss is 0. The network is exactly right. At error equals 2, the loss is 4. At error equals 4, the loss is 16. Loss is a number that depends on every weight in the network. If you imagine a landscape where altitude is loss, each weight is a direction you could step. The question becomes, which direction goes downhill? For a single weight, the weight matrix W, the slope of loss in that direction is the partial derivative, d the loss L over dW. If this slope is positive, the loss rises as the weight matrix W increases, so we should decrease the weight matrix W. If it's negative, the loss falls as the weight matrix W increases, so we should increase the weight matrix W. We always step opposite to the slope. That is gradient descent. The update rule is the weight matrix W gets updated to the weight matrix W minus the learning rate eta times the partial derivative of loss with respect to the weight matrix W. To teach a network, we need to know how a tiny change to any single weight ripples all the way to the final error. That ripple has a name, the chain rule, and before we apply it to a network, let's see it work on something small. To compute d the loss L over dW for any weight in the network, we need one tool from calculus, the chain rule. Let's derive it from scratch on something concrete. Let the variable y equal 2x plus 1, and let the loss L equal the variable y squared. So the loss L is a function of the variable y, which is a function of the variable x. What is d the loss L over dx? Now the chain rule way. D the loss L over dx equals d the loss L over dy times dy over dx. dy over dx is 2, the derivative of 2x plus 1. D, the loss, L over dy is 2y, the derivative of the variable y squared. At the variable x equals 1, the variable y equals 3, so d the loss L over dy equals 6. Multiply. 6 times 2 equals 12. Same answer. The direct differentiation gives the quantity 2x plus 1 squared equals 4x squared plus 4x plus 1, differentiating 8x plus 4. At the variable x equals 1, that's also 12. When change propagates through nested steps, the rates multiply. That's all the chain rule is, and it's the one tool backpropagation uses everywhere. Now we walk one weight's gradient from end to start. This is the keystone once you see it for one weight. Every weight in every network works the same way. Watch the pattern, not the symbols. Now apply this to a real network. The simplest possible. 1. Input the variable x. 1. Weight the weight matrix W1 to a hidden neuron with sigmoid activation. 1. Weight the weight matrix W2 from hidden to output, also with sigmoid activation, and squared loss against a target T. The computation flows forward in 5 steps. Z. The variable h equals the weight matrix W1 times the variable x. The variable h equals sigma of z. The variable h. Z out equals the weight matrix W2 times the variable h. The variable y equals sigma of z out. The loss, L, equals the quantity, the variable y minus t squared. We want d the loss L over dW1, the gradient of loss with respect to the very first weight. By the chain rule, we walk the dependency backwards. D the loss L over dy, derivative of the quantity the variable y minus t squared, equals 2 times the quantity the variable y minus t. Di over g, out derivative of sigma equals the variable y times the quantity 1 minus the variable y. Z out over dH equals the weight matrix W2 because Z out is just the weight matrix W2 times the variable h. dH over Z, the variable h, equals the variable h times the quantity 1 minus the variable h. Sigmoid derivative again, now at the hidden unit. Z, the variable h over dW1 equals the variable x, because Z, the variable h, is the weight matrix W1 times the variable x. Derivative with respect to the weight matrix W1 is the variable x. Pause here. Look at what just happened. Every factor came from quantities the network already computed during the forward pass. Nothing new, just multiplication, walked backwards. Multiply all 5 factors. 2 times the quantity the variable y minus t times the variable y times the quantity 1 minus the variable y times the weight matrix W2 times the variable h times the quantity 1 minus the variable h times the variable x. That is the gradient. One number, computable from quantities we already calculated during the forward pass. So the gradient of loss with respect to a single weight deep in the network is just a product of local slopes, each one reading a value the network already knows. No extra memory, no recomputation. That's why backpropagation is efficient. That was one weight in the smallest possible network. A real network has thousands or millions of weights across dozens of layers. For each weight, the rule is identical. Start at the loss. Walk backwards through the chain of dependencies to that weight. Multiply the local derivatives along the path. The local derivative at each step is cheap to compute. It depends only on what happened at that single neuron during the forward pass. Nothing needs to be recomputed from scratch. The key insight is that we can do this layer by layer, reusing partial results as we go. Compute the gradient at the output layer first, then propagate it backward. Each layer's gradient is built from the one ahead of it. That is why this algorithm is called backpropagation. Errors propagate backward. Everything we just derived for one weight still holds. The only thing that changes is that real networks have thousands of weights per layer, so we bundle the arithmetic into matrices and let the hardware do them all at once. The math is identical. The packaging is different. Writing out one weight at a time works, but a real network computes all gradients simultaneously using matrix operations. Here is the compact notation. Define delta for layer the loss L as the gradient of loss with respect to that layer's pre-activation values. Draw color-coded arrows connecting each matrix term to its scalar counterpart. Grad. The variable y, the loss L, corresponds to the partial of the loss L over the variable y times the partial of the variable y over z out. Sigma prime of z out corresponds to the variable y times 1 minus the variable y. The weight matrix W transpose corresponds to the weight matrix W2. A GPU executes the matrix version in a single operation for the entire layer at once. When you see frameworks use matrix backprop, they're not doing anything new. Every term in that matrix equation is a term we derived by hand in the last block, just arranged so the GPU can multiply them in parallel. Let's watch a network learn XOR from scratch using the backpropagation we just derived. Architecture: 2 inputs, 2 hidden units with sigmoid activation, 1 sigmoid output. Weights and biases degeneralized randomly, small values near 0. The training loop: forward pass, compute hidden pre-activations, hidden activations, output pre-activation, output activation. Step 2, compute the loss. Step 3, backward pass, compute delta at the output, then propagate back. Step 4, compute weight gradients. Step 5, update every weight and bias. The final output for each XOR input: 0, 0 gives approximately 0. 1, 0 gives approximately 1. 0, 1 gives approximately 1. 1, 1 gives approximately 0. The network learned XOR, the problem that ended the perceptron era in 1969. You just watched a network learn XOR in a few hundred lines of code, running in seconds on a modern machine. Why did this take the field 17 years to figure out? 3 reasons. First, the mathematics of backpropagation existed in control theory, in optimization, but nobody had connected it to neural networks. After Minsky and Papert's 1969 book, most researchers walked away from neurons entirely. The ideas were in the library, nobody was looking. Second, compute. Training even a small network required thousands of iterations of forward and backward passes. In the 1970s, that meant hours of expensive machine time for a problem that felt academic. Third, a subtler obstacle that would haunt the next 2 decades: vanishing gradients. The sigmoid's derivative maxes out at 0.25. Stack many layers, and the product of those small numbers shrinks toward 0. Deep networks trained, but slowly, and sometimes not at all. Solving that waited for ReLU activations, better initialization, and eventually much more data. In 1986, 3 researchers, David Rumelhart, Jeffrey Hinton, and Ronald Williams, published a paper titled "Learning Representations by Backpropagating Errors." The mathematics had existed in control theory and optimization for years. Their contribution was recognizing that this machinery could train multi-layer neural networks and demonstrating it. The XR problem, which Minsky and Papert had used to kill the field in 1969, was answered. It took 17 years. From 1 weights gradient derived by hand to 1 million that is backpropagation. But one question is still open. Squared error is the simplest loss function, and we chose it because it was intuitive. There are many others, and the choice shapes what a network actually learns. Next episode: loss functions.